Oxidation reduction reactions is the purpose of this unit. It is our second to last unit, so hip hip hooray. It is the last unit that we'll take a formal test on, other than the final. Oxidation reduction reactions, we will call them redox for short, even though that's like flipping it and it's backwards, but redox is how we normally refer to those. But basically they're reactions where electrons are transferred, okay? In order for them to happen, we'll find out later that one has to gain, one has to lose. Okay, you can't have one without the other. They are, in addition to the 5 we've already studied. Remember when we did types of reactions, we did single replacement, double replacement, synthesis, decomposition, and combustion. Here is the thing. The redox is kind of the umbrella for several of these. Synthesis, decomposition, combustion, and single replacement are all redox. So you might want to underline those and say they are redox. There is an exchange of electrons. Double replacement is not a redox. Okay? And after today, you'll learn how to recognize redox. Today, we're going to be seeing how we can assign oxidation numbers to all the elements in a compound. Oxidation number is a positive or negative number assigned to an atom according to this arbitrary set of rules that I'm about to give you. Okay? Once we assign the oxidation number, we can look at it on the reactant side and the product side and see if that oxidation number changes. If the oxidation number is changing, then we are exchanging some electrons. We're either going to be gaining or losing. Okay? Unlike ionic charges, they don't actually have any physical meaning. It's just a way for us to keep up with how many electrons are being transferred. Okay? Now for the set of arbitrary rules. Okay? And they are in order. See it? I even wrote it big and bold so you could see that they are in order. Use the rules in order. What does that mean? Number rule: 1 is more important than 2. 2 is more important than 3. 3 is more important than 4. Okay? So they trump them. So the first one is the oxidation state of a free element is 0. Why? They haven't done anything with their electrons yet. They haven't taken them or given them, so it's 0. So they have all their electrons and they don't have more than they should. That includes free elements of our Brinkelhoffs, our diatomic elements. Okay? So if you were in a reaction saw O2 by itself, that oxidation state for that would be 0. Are they Brinkelhoffs when they're in a compound? No, they are not. They're what they need to be then. Brinkelhoffs are only Brinkelhoffs when they're by themselves. And of course, in case you forgot what we mean by Brinkelhoffs, what do we mean? Diatomic. 2 of them stuck together. Okay? Rule number 3 says, in compounds, fluorine is always a -1. Always a -1 in a compound. Not the case with chlorine, bromine, iodine, but it is for fluorine. Why does fluorine always get to be a -1? What do we know about fluorine? It's the most electronegative, right? Which means in the battle for the electron, it always wins. So it'll always get that electron. Okay? So it's always going to be a -1 in a compound. Rule number 4 states that oxygen will always be a -2 unless it's in a peroxide. Most of the time, if it's a peroxide, I'm going to tell you, but you should at least recognize this one. H2O2 is hydrogen peroxide. How do I know it's a peroxide? Well, what does normally I just gave you the answer. What does normally hydrogen and oxygen do when they get together? Water. Clearly, that's not water, so it must be a peroxide. Okay. That just recently caught my AP kids. They saw this. And they didn't recognize it as a peroxide. How could I recognize that as a peroxide? 2 oxygen. Normally, sodium would be, and oxygen would be Na2O. So that's one clue is to do that. Okay? So that's, otherwise it's always going to be a -2. So honestly, most of the time we see it, it's going to be a -2 because we don't do too many peroxides. Rule number 5 has a mistake. Okay? Hydrogen is a +1 in a covalent compound, but in metal hydrides, that should be, it's a -1. Okay? Metal hydride, here's an example of a metal hydride. NaH. Nah. Really is, though. Okay? In that case, hydrogen would be a -1. Okay? I skipped rule number 2. Why didn't y'all stop me?
I thought I just figured, but then I was like, oh,
Yeah, I skipped rule number 2. Sorry. Monoatomic ion is the same as its charge. Okay? Monoatomic ion. Meaning, if I have sodium, its oxidation state is going to be the same as its charge plus 1. If it is a group 1 or 2, it's going to be the same as your charge every single time. Group 1, always a plus 1. Group 2 metals, always a plus 2. Your transition metals, however, that's not always the case. You have to look at what it's bonded with. And then the last one, rule number 6, states that the sum of all these oxidation states have to equal the either 0 for an electrically neutral compound, or if it's a polyatomic, they have to equal the charge of the polyatomic. Okay? Okay. So, we are going to do some examples. Lithium. What is its oxidation state? 0. It's a free element. Okay? Calcium carbonate. Okay, calcium is a monoatomic atom. It's also a group 2 metal. So what is its charge? Plus 2. What does the rule say about oxygen? Not a plus 2. It's always a negative 2 unless it's a peroxide. Clearly, that is not a peroxide. So it's a negative 2. So carbon is what we have to figure out. And we base it on what everything else is. Now, I'm going to tell you the easiest way to do this is not in the whole compound. I'm going to say pull this out and do it as its polyatomic. What is that polyatomic ion? Carbonate. And it's a negative 2. So we know that oxygen is a negative 2, right? Always, because that's what the rule says. But how many oxygen do we have there? 3. So tell me, what is 3 times a negative 2? So our total negatives are negative 6. Notice I'm still saying that my oxidation state of oxygen is still a negative 2. I never put the total. I put what it is individually. Okay? So if it's a negative 6, so most, I won't say most people, I'll say a lot of people could look at that and say, if that's a negative 6, carbon has to be a what? Not negative, positive 4. So some people can just look at it. If you are not one of those people and you have no idea where I just pulled that 4 from, I'll show you some simple algebra. Negative 6 plus x has to equal a negative 2. So that means x has to be a positive 4. The reason it has to equal a negative 2 is because the charge of my polyatomic is a negative 2. So overall, it has to equal that.
But I thought it had to equal. Oh, the charge. Oh, never mind. There. Sorry.
Okay. Now, you could do that same thing in the whole compound because you know that's a plus 2, you know that, but then because that's a negative 2, but you really have negative 6, so it just becomes a little bit more complicated. It's better to pull it out of as a polyatomic. Okay?
So you, like, and on any, you can pull out the polyatomic and then do that.
Yeah. Now, if you don't know your polyatomics, that's a problem. But even if you didn't remember that carbonate was a negative 2, you know that it has to be a negative 2 because calcium was a plus 2. Yeah. Okay. So let's do a few more. Okay. Let's keep it on this page. The ones that are on the next page are some examples. Those aren't the ones I'm going to do. Those are the ones I'm going to leave in there for you, like when you're studying for a test, if you want to look over them or whatnot. Okay. Hold on. Boom. Back in business. Okay, so keep it on the bottom page. I'm going to do the examples that are in my PowerPoint, so you should write them down at the bottom. The reason I say write them down on the bottom of your notes is because you have the rules right there and we can refer back to them. Okay? All right. So let's start out with potassium permanganate. So potassium is a group 1 metal, so what will its oxidation state be? Plus 1. Okay? Oxygen, always, according to rule number 4, always minus 2. And I don't care whether you do minus 2 or 2 minus. There is a school of thought that you're supposed to write the minus before or after, depending on whether it's an oxidation state or a charge, but I don't really care. Okay, just put it that it's negative. Okay? All right, so now we have to figure out what manganese is. Okay? So permanganate is that polyatomic. Okay? So if I have 4 oxygen, how many total negatives do I have? 8. Negative 8 is my total. Negative 2 times 4 is negative 8. It's okay. That doesn't even look like an 8. Let me fix that. It looks like something.
Disfigured cobra.
A disfigured cobra. Hey, no body shaming the cobras. Okay. All right, -8. So if I'm just looking at this in my head, I could say, Justin, what does manganese have to be here? That is incorrect. That is also incorrect. Adam? Hi.
7.
What?
What?
Oh, +7. Yeah, manganese has to be a +7.
Because it has to equal -1.
Because it has to equal a -1. Okay? Again, if you can't just visualize that, you'll say -8 plus x is equal to a -1, so x has to be 7. Okay? If it makes you feel better to do the little algebra problem, you can do it. If you can just look at it and say, oh, okay. All right? Yes?
Where did the -1 come from? Is it from the MnO4?
Because it had the overall charge has to equal that.
Oh, okay.
Yeah, because that's the charge of a permanganate. Okay? Again, you could go back and do it in the whole problem if you wanted. It just seems to be kids do a little bit better when you pull out the polyatomic. Now, some of you I know have already talked to last year's pre-AP students, and they've already told you how poorly they did on the redox quiz. So I'm hoping that they scared you sufficiently enough to know that you really got to know how to do this. The quiz is not that hard. Kids either did really poorly or they did really well. And so today someone asked me if I was going to redo the quiz, and I'm like, absolutely not. It's a good quiz. They just didn't know how to do it last year. Okay? Guess what? They figured it out for the test, though, so the test grades were a lot better. So heed their warning from last year and really know how to do this stuff. Now, the quiz is... not just this stuff. There's some other stuff on there. Yeah, not just this stuff. Okay? But, yeah. So you have to know the rules. I don't give you the rules, but once you use them enough, you kind of get to know them. Okay, so now I'm going to erase this, and we're going to do sulfur 3 times. Okay? And what I'm going to show you is that on all 3 of these cases, what is the oxidation state of oxygen? -2. It's the sulfur that's going to change. So we're going to do red, purple, and black for the 3 different compounds. Yes, we are. Yes, we're going to do them all at once because oxygen's not changing in any of those. But first I want to ask you the difference between these 2 things. They're both SO3, without a charge, with a charge. That caught y'all on the nomenclature quiz.
Trioxide.
That is sulfur trioxide. The first one is sulfur trioxide. And then the SO3 2- is sulfite. So just based on that, is sulfur going to have a different charge in those, do you think? Well, yeah, 0 and -2. They got to equal different things. Okay? All right, so since we know that oxygen is a -2, we have a total of a -6 for oxygen. So what does the sulfur have to be there?
We're getting it to equal 0.
You get into needs to equal.
So -8. Wait, so I did that backwards.
6. It's to equal 0.
It's to equal 0, so it's going to be +6.
She's factoring in the 2. We don't factor. Oh.
What do you mean I'm factoring in the 2?
No, she is.
Oh, she
That's
is.
how she got the 2.
Okay. Right? Okay. What about in the next one? There I need it to equal a -2. So it would have to be a +4. So sulfur would be a +4. Because this is still a -6, right? Again, -6 plus x is equal a -2. That means x has to be a +4. That's what they're doing in their head. Okay? They're just looking at it and seeing it. And if you can't do that, then do yourself a little quick algebra problem. Okay? And then the last one, still -2 for oxygen, but what's my total negative? -8, which I need to equal a -2, so what is sulfur?
6.
+6. Okay? Any questions right now? So far, so good? Okay, there's one on the worksheet that I want to do just so you know how to do this. And also I want to mention to you, and you can write this note under the rules if you want, since we're still on that front page, that it is possible, and actually it can sometimes happen, that occasionally you will get a fraction or a decimal number for your oxidation number. So fractions or decimals are possible. And I want to show you an example, and you can just jot this under the note part if you want. But sometimes it freaks people out because they're like, what? It's not a whole number. But if, let's say I was doing C4H10, and what does our rule say about hydrogen? So hydrogen we know is a +1. So we have a total of a +10, right? So what would carbon have to be? We for sure need carbon to be a -10 over here, but we have 4 of them. So this would actually, could be our oxidation state. You could write it as -2.5, or you could reduce that fraction and do -5/2. All 3 of those would be acceptable for carbon. And it's because, obviously, we can't divide that by an even number, right? So there are occasions when you will get a fraction or a decimal. Any 3 of those ways I would accept if you wrote it that way. Okay? So let's do, that kind of will cover what I was going to do on the worksheet, but let's do one on your worksheet. I think you have one in 205, right? Is that one on your worksheet? Okay.
1C.
So we know that oxygen is -2, right? So we have a total of -10. So that means this side has to be a +10, but we have 2 of them, so nitrogen has to be a +5, right? So nitrogen would be a +5. And notice when there are multiple in there, for what I'm saying the oxidation state is, I am stating the individual nitrogen, not the total nitrogen. Because if we were doing this in a problem and we're trying to see if nitrogen's changing, it would really mess us up if we put that the nitrogen was a +10, because it's not. Each individual nitrogen is a +5. Okay?
Do you have to put less on the quiz?
You don't have to, but I prefer you to for your benefit. Yeah. But you don't have to put the plus. But you do have to put the negative, obviously.